Hey everyone, if you've ever found yourself staring at a recursion problem in C, maybe in class or during a tech interview, and just thought, what is going on here? Well, you are in exactly the right place. It can feel super confusing, I get it, but we're going to break it down step by step. And trust me, by the end of this, you'll see recursion as a really powerful tool that you can actually understand and use. So let's get into it.
So here's our game plan. First, we'll nail down the core idea of what recursion even is. Then, we're going to walk through two classic examples, factorial and Fibonacci, to see where it shines and where it can be a real problem. After that, we'll look at how to fix recursion's biggest weakness. And finally, we'll answer the most important question of all. When should you actually use this thing?
All right, let's dive right in. Picture this. You're sitting in an exam, you open the paper, and this is the very first question staring back at you.
What is recursion? It's the classic opener. Go on, take a second. How would you actually put it into words? It's one of those things that's way easier to show than to tell, but you've got to have that textbook definition down first.
So at its heart, recursion is actually pretty simple. It's just a technique where a function calls itself. That's it. The whole point is to take a big, messy problem and chop it down into smaller and smaller pieces until you get to a piece that's so tiny you can solve it instantly.
Every single recursive function you will ever see is built on these two parts. You've got the recursive case, that's the part that does the self-calling, usually with a slightly smaller problem each time. But honestly, the real hero here, the most important part, is the base case. Think of it like the emergency brake. It's the condition that finally tells the function stop, and without it, you're headed for disaster.
And that leads us to the perfect follow-up question your professor loves to ask. It's a real test of whether you get the concept. So, what is the consequence? What happens if you build this thing, but you forget to include the stop sign? You get a stack overflow. And here's why that happens. Every time a function calls itself, it puts a little bookmark in a part of memory called the call stack. Without a base case, it just keeps calling itself, piling bookmark on top of bookmark until it literally runs out of memory. And then, bam, your program crashes. This is why the #1 rule of recursion is always figure out your base case first.
Okay, theory is great, but let's make this real with a classic example, the factorial function. We're going to trace exactly how the computer figures out factorial of 4, and we're going to see that call stack we just talked about get built piece by piece.
Okay, so we start by calling factorial 4. The function looks at the number 4 and goes, nope, that's not my base case. I can't solve this yet. So its instructions say, to get the answer for 4, I need the answer for factorial 3 first. So it calls factorial 3 and just waits. Our first call is now paused, sitting at the bottom of our stack.
And you could probably guess what happens next. Factorial of 3 calls factorial of 2, which then calls factorial of 1. Each new call gets stacked right on top of the last one. Our call stack is getting taller and taller. The key thing here is that none of these functions are finished. They're all just paused, waiting in line for the one above it to give them an answer.
And there it is, the moment we've been waiting for. Factorial of 1 finally hits our base case. It knows the answer is just 1. It doesn't need to call itself anymore. So for the very first time, a function can actually return a value. And this one little return starts a chain reaction, causing the entire stack to start unwinding from the top down.
So as that stack unwinds, the answers get passed back down the chain. Factorial of 1 hands its answer, 1, back to factorial of 2. Now factorial of 2 can finally finish its job, calculating 2 times 1, and it returns 2. That answer goes to factorial of 3, which calculates 3 times 2 and returns 6. And finally, our original function, factorial of 4, gets the 6 it's been waiting for, calculates 4 times 6, and gives us the final answer, 24. See that? The real work only happens on the way back up.
Now for our second example, and this one shows us a really dangerous trap. The Fibonacci sequence seems like it was made for recursion. The code for it is beautiful, it's elegant, it perfectly matches the math. But, and this is a huge but, hidden inside that beautiful code is a massive, massive performance problem.
So here's the trap. To calculate fib5, our function needs to call fib4 and fib3. Okay, makes sense. But now look, to calculate fib4, it also has to calculate fib3. We're already calculating the same thing twice. As you go down the tree, you see it gets worse and worse. We end up calculating the same values over and over and over again. It's an incredible amount of wasted effort. This crazy inefficiency has a name. It's called exponential time complexity, or O of 2 to the n. But what that really means is that for every single number you add to the input, the amount of work the computer has to do pretty much doubles. This kind of solution gets impossibly slow incredibly fast. It's the classic example of where a simple, elegant recursive function is just the wrong tool for the job.
So how do we fix this performance nightmare? Well, there are two main solutions you really need to know for your exams. The first is to just ditch recursion entirely and use a simple loop. That's called iteration. The second is a really clever trick to make the recursive version smarter, and it's called memoization.
So on the left, you've got that pretty recursive code. On the right, the iterative version using a standard for loop. Yeah, the recursive one might look cleaner, but all that repeated work we saw makes it a snail. The iterative solution, on the other hand, is a workhorse. It just uses a loop to build the numbers from the bottom up, calculating each value only once. It's fast, it's efficient, and it just gets the job done.
But let's say you really like that elegant recursive structure, and you just want to make it fast. That's where memoization is your best friend. Think of it like giving your function a cheat sheet. The logic becomes, before I do any hard work, let me check my notes to see if I've already solved this exact problem. If the answer is there, you just grab it. If not, you do the calculation, and then, here's the key part, you write the answer down on your cheat sheet so you never have to calculate it again.
And look at the difference this makes. It's not just a little better, it's night and day. That naive recursive approach is a performance disaster at O of 2 to the n. But just by adding that simple cheat sheet with memoization, we get rid of all the repeated work and bring the complexity way down to a super fast linear O of n. The iterative solution, of course, is also O of n. This just proves how important it is to pick the right algorithm.
Okay, so we've seen recursion can be elegant, but it can also be super dangerous. So this leads us to the most practical, real-world question of all, not just for an exam, but for your career. When is recursion actually the right choice?
Recursion really shines when the problem itself is structured like a Russian nesting doll. Think about a file system. A folder can have more folders inside, which have more folders inside. That structure is naturally recursive. Same thing for data structures like trees. It's also perfect for divide-and-conquer algorithms, where the whole strategy is to break a big problem into smaller versions of itself. In these situations, the recursive code is often way cleaner and easier to read.
On the flip side, you want to avoid recursion when every millisecond counts. If you're tight on memory, or if you can solve the problem with a simple for loop, like we saw with Fibonacci, then the iterative way is almost always better. And this is a big one. If you think that chain of calls is going to get really, really long, the risk of a stack overflow is just too high to justify using it.
So, if you're going to remember one thing from all this, make it this. Recursion is the natural, often beautiful way to solve some problems, but it can be expensive. Iteration is your efficient, reliable workhorse. And memoization, well, that's just smart recursion. It's the hack that can give you the best of both worlds. And I'll leave you with one final thought, something that goes way beyond your next exam. This whole choice between recursion and iteration, it's not just about performance. It's about a fundamental trade-off we make as engineers every day. What's actually more valuable in the long run? Code that another human can easily read and maintain, or code that's been optimized for pure machine speed? The real answer, almost every time, is it depends. Thanks for tuning in.